CPU Central Processing Unit is the primary component of a computer that handles all types of computation tasks required for the operating system and applications to run, and it tries to do so with minimal latency, and it's often referred to as the brains of the computer. Some of the main internal components of a CPU include the arithmetic and logic units, the ALU, which is responsible for carrying out arithmetic and logic operations. This includes basic calculations like addition, subtraction, multiplication, and division. As well as logical operations, the ALU is critical for the execution of most processing tasks within the CPU. The control unit orchestrates the operations of the CPU by directing the flow of data between the CPU and the other components of the computer. The cache is a small-sized type of volatile computer memory that provides high-speed data storage and access to the CPU. It is used to temporarily store frequently accessed data instructions from the main memory, which could be random access memory. And then we also have the memory, which is not part of the CPU but is used to store data in the instructions that the CPU needs to access frequently while performing tasks. We also have multi-core CPUs. So many modern CPUs have many cores, and you may have heard of something like a 16-core CPU, meaning it has 16 cores, each of which can perform a different job while working simultaneously. So what is a core? Each core of a CPU is designed to be a self-contained independent processing unit capable of executing instructions independently from other cores, and this modularity allows CPUs with multiple cores to handle more tasks simultaneously, increasing the overall efficiency and performance for multitasking and parallel processing applications. The arrival of computer graphics and animation resulted in the first compute-intensive workloads that CPUs were simply not designed to handle. For example, video game animations required applications to process data to display thousands of pixels, each with their own individual color, light intensity, and movement. And that's where GPU graphics processing units, as the name suggests, was originally invented to help render images on display devices. Mechanically, a GPU is similar to a CPU in that it is made up of many of the same components such as the ALU, the control unit, and the cache. A GPU can handle very high throughput, and this is due to the enormous amount of ALUs. In addition, GPUs also include hundreds, if not thousands of cores that manage several processing threads simultaneously. And because GPUs are best suited for repetitive and highly parallel computing tasks, people soon discovered that rendering graphics was not the only thing that GPUs were good for. And so GPUs also excel in fields such as machine learning, financial simulations, large scientific computation, and obviously is heavily used in the advancement of AI. So now that we understand how each different processor is segmented, let's figure out what each of these segments are able to hold. 32-bit and 64-bit are terms used to describe the architecture of a computer's CPU and its operating system. These architectures determine how much memory and data the CPU can process at a time, known as memory addressing. Memory addressing is the process in which the computer's CPU and software interact with the computer's memory or RAM to read or write data. Memory addressing involves specifying the location of data in memory, allowing the CPU to access and manipulate that data. A 32-bit system can address a maximum of 4 GB of RAM, so the CPU is only able to access and use 4 GB of RAM at one time. As the 32-bit CPU is only capable of using 4 GB of RAM at once, handling resource-demanding software. A 32-bit system would not be good for running a large spreadsheet, gaming, editing videos, or really anything that involves more than some basic web browsing and word processing. That is roughly how GPUs and CPUs work, but what do the numbers of bits mean? Only very low-budget machines, such as some Chromebooks and older machines, still use 32-bit architecture. A 64-bit system can theoretically address an incredible 16 million terabytes of RAM at once. Obviously, no device in the world comes close to this limit currently and won't for decades to come, but the important thing to note is that it can make use of more than the 4 GB of RAM that 32-bit systems can. 64-bit systems are backwards compatible, meaning they can also run old pieces of software designed for 32-bit systems. 32-bit systems may struggle to run 64-bit software due to their RAM limitations. Each CPU cycle of a 64-bit processor processes 64 bits of data. Bits are queued up in the RAM and await processing and are cycled through in chunks. Since most data is one- or two-dimensional, the bit organization works great. However, this limits everything to binary bottlenecks. The most common solution is batching and organization. However, that too has its mathematical limitations. While effective for low 2D system logic, it lacks the required structure and standards for effective data processing. Our proposed solution is encapsulating the data in SHD CCP packets, which are neural symbolic placeholders for higher dimensional data, allowing extrapolation of multidimensional data without hitting the theoretical limitations of vector embeddings. Traditional data is flat, like a single frame of a movie. By sending calibrated packages of known parameters sequentially, we can create 3D structures with this 2D process. An AI can now perceive the entire story, not just the current state. It will know how a system evolved, and be able to recognize cause and effect relationships through chains of reasoning and grasp narrative behind the data. The structure is more than just data, it's physical representation of a process. Each layer can be a step in an agent's reasoning, creating a buffer of thoughts that is both memory and a logical map. So why would we do this? Modern AIs use data from humans, which traditionally has been in the form of 2D arrays. We can manipulate these arrays into 3D objects, but that is the highest dimension we can add to these arrays. Mapping concepts to points in a vast meaning space, we use vectors or tensors in a lattice structure. AI systems can see similarities in the data structures when they are arranged like this. Google DeepMind new research published a statement: for any fixed embedding dimension, there will always exist retrieval tasks that simply cannot be solved, no matter how much data you throw at them or how long you train. This is actually a mathematical problem, and not something more hardware can solve. When you input data into an AI system, it creates a one-dimension object called a vector in point space. We add another vector, we are able to create a tensor matrix using both dimensions. This allows us to see relations in the data. Adding more creates a 3D object. AI systems analyze these objects for patterns. As you add more dimensions to data, the space expands exponentially, causing all of the data points to become sparse and isolated from one another. This makes the concept of distance or closeness lose its meaning, rendering tasks like finding the nearest neighbor almost impossible. The efficiency of algorithms changes as input size grows. Each line on the graph represents a different order of complexity, commonly expressed using big O notation. As data increases, the time steps required to solve increases in difficulty. No amount of training can overcome this mathematical wall. Eventually, the system chokes on complex queries. The SHD CCP protocol solves this by changing the paradigm. Instead of trying to represent everything geometrically in 3D space, it uses a compact, 64-bit packet that acts as a compressed, neural symbolic hardware-native command for the GPU. This structure compresses many different hyperbolic states into the optimal packet size for CPU and GPU processing. Choosing an O1-constant time algorithm for data structures has predictable and incredibly efficient advantages. In high-performance computing, O1 signifies an operation whose execution time is independent of input size, completing in a predictable number of clock cycles. The AI industry is built on a paradox. Trillion-dollar models are bottlenecked by $100 passing inefficiencies. Every major tech company is hemorrhaging money on underutilized hardware and wasted energy because their data ingestion pipelines follow O(n) complexity. We hold the patent for the architectural shift that solves this problem, moving the industry to O1 constant time data access. Our core asset is the first mover, foundational patent covering O1 data compression and streaming. This is not a patent on a single application, but on the fundamental mechanism that every major technology company will need to adopt to remain competitive in the next decade of AI. This creates a powerful, defensible licensing opportunity and positions the company as a key enabler of the future of computation, making it an acquisition target for every major player in the cloud and AI space.